All right, this video is going to be on those higher order derivatives, specifically focusing in on the first and second derivative and how it relates to movement. And we call these problems rectilinear motion. They also talk about particles moving left and right, up and down in the XY plane, which is sometimes called a rectangular plane, which I think is why they call it rectilinear motion. So first, just to make sure that we have all this notation down for the different derivatives, we have f is the function, f prime is the first derivative, f double prime is the second derivative, f triple prime is the third derivative, and then after that they stop using the Roman numerals and they write it like this. And to differentiate between an exponent, although truly I don't know that I've ever seen anyone write like a function to the fourth power, but to make it look different, they do put parentheses around that. So here's our fourth derivative, and then I'm going to say dot, dot, dot. We can keep going up to the nth derivative. Now, when we talk about particle motion or rectilinear motion, then the original function we call the position. That's the position of the particle, s of t. I don't know why they use an s. Position, s, I don't know. Then we have the velocity. This is what I've talked about as if you're driving a car and you look down at your speedometer, this is just how fast you're going. And then acceleration is the second derivative, and we write a of t for that. So here we would say that the velocity is the derivative of position. The acceleration is the derivative of the velocity, which is the second derivative of the position. So this stuff is what we're going to be focusing on today. Okay, before we go on to that though, I just want to do a general example using all this derivative notation here. So this example says find all derivatives for y equals x to the third minus 6x squared minus 5x plus 3. And so when it says find all derivatives, that means that you keep finding derivatives until the function like zeroes out, basically. So y prime, that's our first derivative. We have 3x squared minus 12x minus 5. Our second derivative, 2 times 3 is 6, 6x minus 12, the 5 zeroes out. Third derivative is just 6. And then the fourth derivative is where we're going to stop, and that's a derivative that equals 0. So that's us writing out all the derivatives for that problem. Okay, let's move on to rectilinear motion specifically. So I know I already wrote this as a title, but I'm going to write it again because now we're getting specific. Okay, so for rectilinear motion, we're going to say it's got an object that travels in a line. S of t gives the coordinates of the point. And they often call the point P. We already said velocity of P is v of t, but I'm going to go ahead and write it again. And v of t is the first derivative of the position. The speed of P is the absolute value of velocity. So if you guys have taken, I believe it's physics that they talk about it the most. I don't think they discuss it in chemistry. But if you've taken physics, then you know that velocity is not just how fast you're moving, but it's also directional. So if you are moving towards the left, you would call it a negative velocity. Towards the right would be a positive velocity. If you're talking about like the x, you know, going left and right, if you're going up and down, going up would be positive, going down would be negative. So velocity itself has a number that's like the magnitude of the number, that's like how fast you're moving, but also a direction, that's the positive or negative. So when you talk about speed, you just want to strip away that sign and give it an absolute value. And then you're not talking about the direction anymore, you're just talking about how fast you're moving. All right, the acceleration of P is A of t, which is the derivative of velocity, which is the second derivative of position. All right, and then this one is the kicker. This is the one that messes with everyone's brains. This one shows up on FRQs. This is the one that we have to memorize. So the particle itself is speeding up when velocity and acceleration are the same sign. So if the velocity is negative and the acceleration is negative, it's like slowing down in the backwards direction. The negatives cancel out, it makes a positive. I don't know. This one is kind of feels a little bit abstract to explain, but if both of these numbers are positive, then the effect that it would have on the particle if you were watching it is that it would look like it's moving faster. If both of those numbers negative, it would have the same effect. You're going to see the particle slowing down. And you'll notice I'm not saying accelerating and decelerating because that's going to be the sign of A of t. I'm talking about what the particle looks like if you were to look at it. I'm not using acceleration. I'm just saying, is the particle moving faster or slower? It's slowing down when the velocity and acceleration have opposite signs. All right, and that's something that I think is a little bit intuitive, but also feels a little bit abstract. Definitely highlight that, put stars around it, something to draw your attention to that, because that is a very common question, and it's easy to miss. All right, so we're going to go ahead and do some example problems with this. So the first example gives us the position of the particle, and they tell us that the position is t to the third minus 12t squared plus 36t minus 20. And what they want us to do is describe the motion of P on the interval -1, 9. And this is a closed interval. We're including what's happening at time t equals -1, so at -1 seconds, and 9 seconds, or these could be minutes or hours. So the first thing I always do in these problems is I figure out what my velocity is and what my acceleration is written as functions. So we have s of t, our velocity equation is going to be 3t squared minus 24t plus 36. A of t is going to be 6t minus 24. All right, and then after that, what I typically do is I look at where the velocity equals 0. So if you think about velocity being what happens when you look down at your speedometer, if you look down at your speedometer and you're seeing 0, that means that you're not moving. So that's an interesting piece of information if we're describing the motion of the point P, is that we want to know when P is not moving at all. So I'm going to say V of t equals 0. Here we're going to say particle is not moving. And I'm going to go ahead and solve that problem. So 3t squared minus 24t plus 36 equals 0. This is a factoring problem. I can see that each of the terms has a GCF of 3. And now I'm looking for two numbers that multiply to 12 but add to negative 8. All right, so I have two times. I have 2 and 6. So at those two moments, the particle completely stopped moving. It wasn't moving at all. All right, now what we're going to do next is we are going to set up a sine chart because we want to see where the velocity is positive. That's going to be where the particle is moving to the right or moving up and down, or to the left if it's negative. Now, I didn't put this in the instructions. Typically, they describe these particles as moving on the I think they say the x-axis typically is how they say they're moving. So they would typically be moving left to right. I think that's a valid assumption you can make that that's what they're doing if they didn't describe it. Really, I should have put that in the question. I'm sorry. I don't have a lot of space. If you want to go back and write it that the particle's moving left and right, you can go ahead and do that. So I'm making a sine chart. This should be giving you some flashbacks from the summer assignment, and you can kind of see why I made you do it on the summer assignment. So at 2 and 6, the particle is not moving left or right because it is completely stopped. All right, so now what I want to do is I want to take a number that's in between -1 and 2, and I want to plug it in and see if it's going to give me a positive value or a negative value. So I'm going to go ahead and take 0 and plug it in because that's easy. So I've got 3. I'm going to show you guys how I do this where I don't have to actually think too much. So 3 is a positive number. 0 minus 6 is a negative number. 0 minus 2 is a negative number. So if I multiply a positive times a negative, I get a positive. So that means that between -1 and 2 for the time, the particle's moving to the right. Pick another number. So I've got a positive 3. 3 minus 6 is negative. 3 minus 2 is positive. That's a negative answer. Choose 7. 3 is positive. 7 minus 6 is positive. 7 minus 2 is positive. Okay. It is very typical on a sine chart like this for the intervals to alternate, but you can't assume that will always happen because it won't, so you'll get half your problems wrong then. All right, so now we're going to describe some of the movement of the particle. We can say that the particle is moving right and I'm going to include the -1. And it moves to the right up until 2. I'm not including 2 because it wasn't moving at 2 at all. And then I'm also going to say the second interval from 6 to 9, I'm going to include the 9. All right, moving left is from 2 to 6. Okay, so we have some descriptions there. Now let's go ahead and move on to the acceleration. So next I'm going to go ahead and set the acceleration to 0. That means that if you look down at your speedometer, you have your cruise control set, you are going 60 miles per hour, you're not speeding up, you're not accelerating, you're not decelerating, you're just consistently going the same speed. That's what that means. So here we're going to say speed is constant. All right, so I'm going to take my acceleration equation, 6t minus 24, set it equal to 0. You can solve it, but I like this in factored form because when I do my sine chart, it's a little bit easier to plug numbers into to figure out the sine. And when I say a little bit, I literally mean just a very smidge. Easier, but I like to take all the e's that I can get. So again, I'm going to make a sine chart right here. So I've got the 4, the -1, and the 9. I just want to see when I'm accelerating and decelerating. So I'm going to choose a number that's between -1 and 4. I'm going to go ahead and use 0 again. 6 is positive. 0 minus 4 is negative. So there's our deceleration time period. And then a number that's bigger than 4 but less than 9. I've got 6, which is positive. 5 minus 4 is also positive, and that's a positive. So now I can make those conclusions. Decelerating is from -1 to 4. I'm not including 4 because the acceleration was 0. The speed was constant at 4 exactly. Accelerating is going to be from 4 to 9. I'm including the 9. I am not including the 4. All right. Next, I'm going to go ahead and figure out when the particle appears to be speeding up and when it appears to be slowing down. So what I do for this is I kind of combine the two different sine charts that I did together. So the first one had a 2 and a 6. The second one had a 4. I'm going to go ahead and put my signs for the velocity on the top. So it was positive from -1 to 2. It was negative from 2 to 6. It was positive from 6 to 9. Then I'm going to go ahead and put my acceleration on the bottom. It was negative from -1 to 4 and positive from 4 to 9. So now I can label when it was speeding up and slowing down based on the signs matching or being opposite. So here we've got speeding up and speeding up. So we have the interval from 2 to 4 and 6 to 9. And notice that for all these numbers where I have the zeros, I'm putting parentheses there. But for the 9 that did not zero out for acceleration, did not zero out for velocity, I'm including that number. The slowing down was from -1 to 2 and 4 to 6 because those are the two places where my signs are opposite. All right, the next thing that we're going to talk about is the total distance that was traveled. So if you look at this, we can see that the particle is moving to the right, then it stopped, then it moved to the left, then it stopped, then it moved to the right. So if we want to talk about the total distance, we know that at some point, if it moved to the right and then moved to the left, the particle had backtracked, gone forward and backwards. So we want to figure out how far it traveled here, how far it traveled here, how far it traveled here. We want to add all those values together. We don't want to say you walked this direction, then walked that direction, and you only ended up however far away from your beginning point. So the way that we calculate total distance is we make a table of values. So I'm going to have my time, and then I'm going to have my position. So the starting time was -1, and then the velocity was 0 at 2, the velocity was 0 at 6, and then my ending time. So these two numbers are important. This is when the velocity equals 0, which is the moment, if there's any moment where the particle is going to switch directions, that's when it's going to be. So if I plug -1 into the function, and I'll save you guys some time, if I plug -1 in, I get -69 is the position. So you could say it's 69 units to the left. Then when I plug in 2, I get 12. When I plug in 6, I get -20. When I plug in 9, I get 61. And again, to get those numbers, I'm just taking that position equation and figuring out where the particle is, thinking about it in terms of being on the x-axis, having moved to the left or right. So we started at left 69 spaces, and after those 3 seconds have passed from -1 to 2, the particle has moved 81 units total. And then from 2 to 6 seconds, it moved from 12 left all the way back to -20. That moved a total of 32 units. And then from -20 to 61, that moved a total of 81 units. So if I want the total distance, I just have to add those things together, and I get that my total distance is 194 units. You can put UN for units if you want, but you don't have to. So that's how we calculate the total distance. Now, the displacement is talking about something different. It's still a distance, but it just talks about how far you are from where you started. So total distance is how far you went. that's like you've got the speedometer, not the speedometer, the odometer on your car telling you like how many miles you've driven. Displacement is saying like, oh, if I drive to work, I'm this many miles from home. That's how far from home I am. But if I look at my Google Maps on my phone as I'm driving, it's not going to tell me how far I drove that day. It's just going to tell me how far I have to go before I get back home again. That's what displacement means. So displacement is very easy to calculate. We just do the end position minus the beginning position, and that will tell us how far we are from where we began. So we're going to say 61 was the end, minus negative 69 was the beginning. So the displacement at the end is that you are 130 units away from where you started. So these are some typical questions we have with rectilinear motion. You're going to have the green sheet, which just has a lot of these things on it. You're definitely going to want to have that, put it with your other cheat sheets so that if you brain fart on any of these things, you can use it in a testing situation.